Okay, hi everyone. So today I'm going to solve for you the binary search tree tutorial. So let's start this here. Okay, so what are we asked here? So it's just telling us that we have a map ADT and we want to have three implementation of get. And what did we say get is? That get is like a search. So we want to search for a specific key, K, and then put is that we want to put the value V, which has a key K. Usually, if the same key exists in this, wherever we want to put it, in the list or tree or whatever data structure that we're implementing, if the key exists, we're going to update its value. If it doesn't exist, we want to insert this key and the value. Remove key, we want to remove the key and value. So now, why? So if you remember map, something very important in map, it's that it has unique keys. So if I want to start with the get, right? So I have three things. I want to do it with the unsorted linked list, sorted array, and binary search tree. In this case, if I want to do unsorted linked list, we explained in class is that if we want to search, we're going to go off n. Anyway, if I want to search for this key, I need to come because this is a linked list. Now, if I want to put this key, the same thing, I need to go through the whole linked list, the same thing for the remove. You can refer back to the lecture and if there's anything not clear here. Now with the sorted array, what did we say? If I want to search normally in an array, um, usually it's O of n. But here in this question, we're asking you, assume we employ the most efficient known algorithm. And the most efficient known algorithm for search in a sorted array, we covered it in class. It's what? It's binary search. That's why we're going to say here it's O of log of n, not O of n, assuming that we implemented the most efficient known algorithm for us. Now put is going to be O of n again, because even though I know the index, for example, because it's sorted array, I have to, it's a sorted array, so I have to move everything when I'm doing it. So it's an array. Let's say I want to insert something here, so I have to move all of these so I can have a space here. The same thing for the remove. Let's say I remove this one, I have to move everything. So it's going to be O of n. Now with the binary search tree, what is the big O of the worst case complexity? Worst case for a binary search tree. Is it O of log n? No, because if you remember, we said when it comes to the binary search tree, it is always O of h, O of the height. The best case for the height is usually a balanced tree. For example, something like this. That would be a balanced tree. So the best case is a best tree, which is going to be O of the height. In this case, what is the height here? Is a log of n, as we explained. But the worst case is what? Is when we have a worst binary search tree, which is a skew tree like that. It's all on one side. In this case, I'm going to end up with O of n. So please make sure you know the difference that a binary search tree worst case is going to be O of n because we're going to be doing the worst tree. Okay. So as we said here, now let's go for the next question. So all of these are from midterms. So everyone who's asking me what would they expect in the midterms is we're solving already for the heaps for the priority key. We also solved exercises from previous midterms. The same thing here. So we're going to be expecting something like this. It's saying this is a binary search tree. What is the definition of a binary search tree, guys? That everything here is less, everything here is greater. Not just for the root, even any node, and everything on the left is usually smaller than this node. Everything on the right is usually what? Greater. So this is the definition of a binary search tree. So here's telling me show the tree after inserting 7. Whenever we want to insert something, always we have to start from the root, guys. So I come here, I say, is 7 less or greater than 35? 7 is less, so I'm going to go to the left. I'm here, is 7 less or greater than 18? It is less. I'm going to go this way. Is 7 less or greater? Again, 7 is less. So I'm going to go here. Now, is 7 less or greater than 6? Of course, it is greater. So I'll end up with 7 here with 2 dummy nodes if I want to add the dummy nodes. So the 7 will be here. Correct? So let's just erase these now. And that will be my 7. Now, it's asking us show the tree after deleting key 35. So let's see after deleting key 35, which is this one. I deleted 35. We said whenever we're deleting a key that has 2 children, what can we do? Usually, you can look at the in order traversal. So what is the in order here? So let's do a practice for the in order also, because it's something important that you may get. In order is what? Left visit right. So that means my in order will be left visit right. I'm going to go to the left. I'm here again, left visit right. I'm going to go to the left, left visit right, left. So left visit right. There's nothing on the left. I need to visit now, so I'm going to do 6, correct? And then what? 7. Then I'm going back now to the visit, 10. Now, when we're doing the in order traversal and we have the keys, not the values, we have the keys. The in order is what, guys? It's always lists things in the ascending order. That means I don't even have to follow the left visit right. I know that if this is a binary search tree for sure, if I'm sure that this is a binary search tree, technically it's just in the ascending order. So it won't be 6, 7, 10, 15, 18, 21, 30, and then here I'm going to put the 35 back. And then what else? 50, 56, 60, 62, and then 76. Correct? Okay. So that what did we say in class? We said that usually if I want to delete something, I always have 2. So that's my 36 that I'm deleting. I have 2 options. Either replace it with the one before it or the one after it. So I can either have the tree with 30 here, or I can have it with the 35. So what would I have? I will have 30, let's say here. Then I'll move the 21 here because why? There's only one child. Or if I decided to take the 50 in this case, the same thing, I'll move the 56 instead. This is one of the solutions, guys. Another quick method is what? Is I can look at the rightmost node in the left. So if I'm looking at the left, if I want to choose something from the left, I will look at what is my rightmost, not the last element, the rightmost. So if what is the rightmost? This is the rightmost. Or if I'm looking on my right, I can look at the leftmost, which is this one. This is like a shortcut, but technically you can just do the in order. It will be enough. So let's take a look now. As you can see, we have 2 options. We have either the 30 or the 50. And another thing, make sure in the midterm, let's say you got one of these solutions. To know for sure that your solution is correct, do another in order. Or you don't have to even do in order. Just check, look at the node. Is everything on its left still less than the node? Yes, so 21, 18, all of these numbers are still less than 30. And then you look here, 60, 50, 56. Yes, they are still greater. You look at the 50, everything here on the right of the 50 is what? Greater, which is 60 and 56. So that's another way to check if you're, or you can do the in order and you have to stay with the ascending order. Okay, let's move to this. So question from 2017. Here again, we're saying consider this binary search tree and how many comparisons are done when searching for key 66. Now I want to search for key 66. So I want you to tell me how many comparisons we're facing here, we're going to do. Again, from where do we start? We start from the root. So I'm here. So that's 66. That's my first comparison, correct? Okay, so it's greater. I'll go here. 66 is here now. Another comparison. So that's 2. It's less, so that's 66 is here. That's a third comparison. So it's greater, I go here. That's 66. Do I stop? Is it 3 comparisons? No, because I still need to compare with this one to check if I find it or not. So that's how many comparisons? We have 4 comparisons. Now, if you're looking at the pseudocode or you're looking at the Java implementation code, which you can find on Brightspace also, you're going to know that usually from a code perspective, if I want to compare, I'm doing more than one comparison because the first thing I'm checking is 66 equal to 40. If it's not equal, else if, is it less, then go to the left, else go to the right. So that means I'm doing technically 2 comparisons per each node, but here what we're asking is how many comparisons. That means my 66, it's being compared to how many nodes technically. It doesn't matter code-wise how many time I'm comparing the same node. So in general, we're saying this number 66, how many time how many nodes I'm comparing it to it. So I'm comparing to 40, then I'm comparing it to 69, to 54, and then to 66. Now, how many comparisons are done when searching for the key 5? So let's check this. Okay, so for key 15, sorry. So 15, I'm here, that's 15. So I'm comparing it with 40, that's my first comparison. I'm going here, that's again, I'm comparing it with 25, that's 2 comparisons. It's less, so I'm going here. That's my third comparison. It's greater than 11, so I'm going here. And then what happens? I'm going to compare it with 22, and then it's going to be less, so I'm going to be here. Now you have 2 choices. Both of them are correct. You can say 4 comparisons because you compared with 40, 25, 11, 22. That's 4. Or you can also say 5 because you compared it with this dummy node and it was null. So it's either 4 or 5. Insert a new node with key 60 and show the resulting tree. Now, you may draw on top of the given. Okay, so insert a new node with key 60. Let's get a new color. Okay, key 60. So I'm here, that's my 60. Is 60 greater or less? It's a greater, so I'm going to go here. Correct, 60 is less than 69, so I'm going here. It's greater than 54, so I'm going here. Now, is 60 less or greater than 66? It's less, so that's my 60. It can't get easier than this, guys. So again, these are midterm exams. So if you understand the difference between the type of binary trees, is it a complete binary tree, is it a perfect binary tree, is it a binary search tree? If you know the difference between these, you know the difference between a heap and a binary search tree, then you can answer, you can solve any questions, any question. Okay, as we said, this can be 5 comparison here. We just said or 4 is also good. Then we have this pseudocode, guys. You can check it. I'm not going to um, solve it for you because you can check it. You can even put it on actual Java and writing in Java and understand more and debug it if it's not very clear to you. But the idea here is that we're giving you some functions, and we're telling you we want give us a pseudocode or Java code for a method that computes the maximum value of a key stored in a binary search key. I want to compute the maximum value, correct? So you can say first you call the root function. Why? Because the root function returns the root node of the tree or null if the tree is empty. You're going to check now if the right of this node is equal to null. Why am I checking the right node, the right child, not the left? Because I'm searching for the maximum. And binary search tree, always everything on the right is greater than the node, correct? So I only need to go, it's either the right, I don't have any right children, so I'm going to return that this node is the maximum node, correct? Because I don't care, even if I have nodes here, I don't care, because always this is going to be less than the node. Or if they have children, I'm going to continue doing recursively. So while right of the node is not null, then keep calling the right node, correct? Until you reach a point where there's no right children anymore. Or we can do it without dummy nodes. There's not a big difference. Now, if the tree has n nodes and height equal 2 log n, what is the big O running time of your max key algorithm as a function of n? What is our max key? That's the max key, correct? So that's my max key here. So what is the max key algorithm as a function of n? Because the height is 2 log n, so if I say the height is O of h, so I can say O of 2 log n, which is O of log n. Okay, guys, so I think that's it for this tutorial, and we'll see you after the reading week.